All right, everyone. So while you guys are getting settled, maybe we'll go ahead and get started. Um, and before I begin, a couple of quick things. Of course, we have quiz 3 this Friday. So I'll post a sample quiz right after the class, and make sure you take a look at that quiz. I think mainly it's on Castigliano's theorems for beam frame type problems and the force method that we've been talking about. So homework 5 and 6 essentially. None of the MATLAB portions will be on this quiz, but as I mentioned on quiz 4 and on the final exam, you might have some small problems where at least the knowledge that you'll need to have for the MATLAB problems will be needed. Uh, so um, let's actually jump back into this computer program for method of joints that I was talking about last time. And then I've just sent out a much bigger handout for computer methods for indeterminate trusses. The program, by the way, anybody tried to run the program that I posted on Blackboard? There is a MATLAB program on Blackboard that solves determinate trusses, which actually you can use now for solving indeterminate trusses, because essentially for solving indeterminate trusses, we break it down into a system of determinate truss and a redundant truss, and then superimpose them too, right? So you can still use that program. I'll also give the program that I've just for the handout that I've just handed out, which is indeterminate trusses. So first, let's make sure we understand how the program to solve determinate trusses works. And then based on that, we can, I'll talk more about the program to solve indeterminate trusses, because that's a fair bit more complicated than the determinate trusses. And none of this is in your books. So I think you should rely on my notes. And then, of course, if you have questions, you need to bring it up in class, and also post on the discussion forum. All right, so just to recap, we said that to solve any problem with a computer program, what we need is an algorithm on one side and an input file on the other hand, so that we can apply the same code to multiple different types of input files, and we don't need to write a new code every time we want to solve a new problem. And one of the examples that I was giving you was for the method of joints. And by the way, the single page handout that I sent around does have some overlap with a previous handout that I might have given you. But in this new handout, you can either replace that. I think it tried to clarify a couple of steps in there. So I'll talk about that as we go along. So the idea for the method of joints, as we said, was draw free body diagram of all joints, write equilibrium equations for each joint, and then just solve. And the trick really is, how do you automate this process? We all know how to draw a free body diagram for joints and write equilibrium equations for all these joints, but how do I get the computer to do it automatically for me? That's really the trick here. So I mentioned that if you look at a typical truss, this typical truss, for example, right here, and if we draw the sequence of free body diagrams for all of these joints and write out the equilibrium equations for these joints, we start seeing a pattern. And really being able to see this pattern is really what is needed to be able to automate all of this process. So the pattern that I see here is that in any equilibrium equation, there are multiple entries in any equilibrium equation. So for example, for this joint 1, there is an entry there in joint 1 due to an external reaction. So if a particular joint has any external reaction, you can expect there to be an entry due to an external reaction. There is an entry due to force in element A. Why? Because element A is connected to node 1. Similarly, there is an entry due to element B, because element B is also connected to node 1, but there is no other entry out here. So in general, if you look at any one of these equations, you'll see that there might be an external reaction entry in that equation. There might be entries due to elements that are connected to that node. And finally, there might be an entry due to a load, an external load that is applied at that node. So for example, this node 2, which is up right here, there's an external load of 10 kilonewtons applied to it. So we need to add all of those forces to the equilibrium equation of that node and set that equal to 0. So we already start seeing some pattern out here. And if you look even more closely, and then maybe I'll tell you a little bit about what these coefficients are first. So if you look at node 1, there is a force coming on node 1 due to element A. And this coefficient A1x, all that it represents is the direction, the x component of the force at node A. So clearly, if you look at this free body diagram, FA is pointing to the right. And in general, if you go to some equation, equilibrium equation for a node, that FM might be pointing in some other general direction. Is there a way to automate calculation of this A1x or B1x or all these coefficients? Can you think of a way to automate calculating this coefficient? Essentially, this coefficient is trying to find out what is the x component of this force. What do you think there would be a way to automate that? If I'm telling you that node, for example, let's say this element C is connected to node 2 and to node 3. Using that information, we should be able to determine what force this element 2 is going to apply to node 2 and what force this element C is going to apply to node 3. Is that right? Just by knowing the orientation of this node, of this element, I should be able to determine the direction of this force at node 2 and at node 3. That's one point. And the other point is that if you look at any particular element, so for example, element A out here, this element A occurs exactly 4 times in this entire set of equilibrium equations. It occurs once here, once here, once here, and once here. If you list out all of the equilibrium equations for this truss, element A would not occur anywhere other than these 4 locations. Can anybody tell me why? Why does element A occur only in equation 1, 2, and 3, 4? Drew? That's right. So element A is connected to node 1 and node 2, right? And it means that it will contribute to the equation of equilibrium for node 1 and node 2. Further, element A in particular is actually oriented along the x direction, so the y contributions are actually 0. But in general, for example, nodes, this element C is connected to nodes 2 and node 3, and clearly it would contribute to x and y both at node 2 and x and y both at node 3. But in general, any element is going to contribute at exactly 4 equations, right? And how does it contribute? That contribution can be determined from this free body diagram. So if I have an element M that is connected to node I and node J, and assuming that this element is going to be in tension with the internal force Fm, that Fm is going to be opposite on the nodes. So for example, to node I, the direction of this Fm can be determined simply by the geometry of node I and node J, and which is what I've written out here. If you look at this vector Mi, this vector Mi is a unit vector that points from node I to node J, and that Mi is has two components, mix and miy. These would be the two direction or the forces, direction of those forces, mix and miy. So if I can calculate these two components of the unit vector at I, these would be mix and miy. These would be the actual coefficients that would go into the equilibrium equation for node I and node j due to element m. Does it make sense? So I can do this for all the elements in the truss, right? I calculate mi, which is the unit vector pointing from I to j. And similarly, I calculate mj, which would be the unit vector pointing from j back to I, because fm on I is acting in this way and fm on j is acting the opposite way. So length of this element is basically just square root of sum of squares. So once I can calculate all of these coefficients, I can list them in this table. This is just a table of member properties. So I have 7 members here. I know member A is connected to nodes 1 and 2. Mix for A is 1 and 0. Why is that? Because at node 1, it is pointing in the positive x direction. It does not have any component in the y direction. At node 2, it would be pointing in the negative x direction. That's why I've also written it as minus mjx and minus mjy. If I know the unit vector at mi, mj is just the negative of that. Okay, so these would be the 4 values that would go into the equilibrium equations, which is what I had shown you last time as well. If you look at equation 1, this 1 times this fa is the contribution of m1x. Okay, and similarly for node 2, the contribution of the same fa is minus 1. So if you look at this first entry, that first entry is going to multiply this fa out here. So element A, which is connected to nodes 1 and 2, contributes to these 4 numbers and nowhere else. Similarly, element B contributes to node 1 and node 3. Let's check that. Element B is out here, contributes to node 1 and node 3. And clearly, x component is 0, y component is minus 1. Similarly, element C contributes to nodes 2 and 3, which is out here. The coefficients are listed 3 over 5 and 4 over 5 because it's a 3, 4, 5 triangle. And similarly, if you verify, you can go on and verify element D, E, F, G. For any element, it contributes to exactly 4 places in this matrix. Okay, and this is the trick really to automating the process of generation for equilibrium equations. This tells me that to generate this matrix, all I need to do is to loop over all of my elements. I have 7 elements, A, B, C, all the way to G. If I loop over all of my elements and put some value at exactly these 4 places for each element, then and of course add any reaction terms to this matrix as well, then these two things put together, loop over all the elements and loop over all the reactions, that will construct this matrix of coefficients that are of equilibrium equations really. This is just the matrix of equilibrium equations. And on the right hand side, I'll add any external forces to the correct degree of freedom. So once I have that, once I have this matrix, once I have the right hand side, I can solve for all of my unknowns. I can let MATLAB solve for all of my unknowns. Does that make sense? So really, once you are able to construct this matrix automatically, keep in mind, by simply looping over the elements and looping over the reaction points. You have this matrix, you have the right hand side vector, solve for n using MATLAB. And that's essentially what this MATLAB program that I had given to you is doing. So very quickly, I'll kind of outline the steps there without going into too much detail of the code. This on this MATLAB program, this file that says statically determinate truss 2d.m. This is the main file. Statically determinate truss 2d.m. Okay. And if you look at the first couple of lines in that file, they're exactly like you would expect. Clear all, close all, and so on. Define some tolerance and get the input. So I'll maybe make some more annotations to this file. These two lines, get input from user. This is just calculate element lengths, because later on we'll use the virtual work method where we will use these element lengths. Where anybody remember where we use element length in the virtual work method? Great. For the real displacement, NL over AE, right? We need that L there. So calculate element lengths. This line is just plot to check. And this one statement right here is a function call. It's a function call to solve truss 2D. What does it need? It needs information about the nodes. It needs information about the elements. It needs information about boundary conditions, essentially supports, and it needs information about loads. So if I provide input, so this is a function call to this function that I'll discuss in more detail. You tell it where the nodes are, what nodes are connected with the elements, what are the boundary conditions, what are the loads, and the output from that subroutine is two unknowns that we are looking for. We are looking for element forces and support reactions, right? These are, if you look at that matrix, the element forces are right here, FA through FG, the 7 element forces, those are unknowns, and the 3 reactions, those are unknowns. So the output from that subroutine, given nodes, elements, boundary conditions, loads, and so on, the output should be these unknowns. That's all that this particular subroutine does, okay? So this is pretty much the most important call in this entire program. Once you have that, the last line out here, plot output. So essentially this entire program is nothing but this one line call to the correct subroutine. So let's take a look at how this subroutine works. So note that this is the solve truss 2D. That's the most useful subroutine in the entire code. And as I said, the input to this subroutine is nodes, elements, boundary conditions, and the output, there are 4 outputs. But here I'm calling it only with 2 outputs. Okay, I'm saying when I call it only with 2 outputs, I'm saying that I don't need these other 2. Okay, but if I have some other variables also here, then I'd be using these variables also. So let's see how this works. Essentially in this, as I said, first thing to do is to create an empty A matrix. So this is an A matrix. It's initially full of all zeros. So for this particular truss, this would be a matrix of size 10 cross 10. Correct? So first I'm making a matrix which is of the correct size, fill it up with zeros, and then I'll fill it up with correct entries. So uh, this is a matrix, and I've also constructed a right hand side of 10 cross 1, which is of the correct size. Now, as I said, this is the loop. This is the loop which runs from this for statement all the way out to this end statement. So from for I equal to 1 to number of elements, all that this loop is saying is do something for each element that you have in your truss. For this particular truss, there are 7 elements. So this loop would repeat 7 times for element 1, element 2, element 3. You'll do this again and again for 7 times. And let's see what we are doing. We are calculating where node 1 is. We are calculating where node 2 is. We are calculating the element length. And we are calculating these two values, which is M ix and M iy. Okay. So these two lines, we are actually going into the A matrix, and we are plugging in those mix and miy in the correct location. Similarly, these two lines, we are going and plugging in minus miy, which is equal to actually, so I'll write that mjx, mjy. So negative of those two values would occur here. At the end of this loop, one element has been taken care of. There would be 4 values, so one element has been taken care of. Then this loop repeats, does the same thing for element 2, this again, element 3, element 4, and so on. At the end of this loop, we would have this part of the matrix done. Right? We would have 4 entries in each column for each element. We would have all the way up to this matrix completed. And the only thing remaining would be the number of reactions. So let's see where that happens. And add contributions of the support reactions to the nodal equilibrium equations. So this for loop, this is yet another for loop. What this is saying is for I equal to 1 to number of boundary conditions I have. So if I have 3 boundary conditions, this loop would repeat 3 times. And it would go find which node it is, find which direction it is, and it would apply the number 1 at the correct location. And what I'll do is I'll run this code in a little bit and show you exactly how this is getting built. So maybe this is a good time to do that right now. I'll go to the main code. I'll put a breakpoint at this line that I'm at the solve truss 2D line. I click run, and I'll choose the input file 4, which I think is posted on Blackboard as well. This is the input file for the truss I'm showing. So open that. This is the truss we have. So I'll go back to this guy, and I'll say step in, and in this I'll put a breakpoint here, and I'll say run to that. So if you look at the matrix right now is all zeros, 10 cross 10, completely full of zeros, because that's what I did here. I initialized the matrix. The right hand side is 10 cross 1, all zeros. And I have just started this for loop. So the value of I would be what? Would be 1. So I'm looking at the first element. This first element is, let's look at this element. So the elements matrix in this particular case, there are 7 elements, 7 cross 2. Clearly the first first element is connected to nodes 1 and 2. So its contribution would go where? Which rows would this element 1 contribute to? Rachel, any guesses? Miles? Rows 1 and 2 because of node 2, oh sorry, node 1, and rows 3 and 4 because of node 2, right? Because if you remember, we said um, each element is going to contribute to 4 locations. So since it's connected to nodes 1 and 2, it will be contributing to 1, 2, and 3, 4. Okay, and let's go back to this guy and let's make sure that's exactly what happens. So I'll step through here, calculate element length. For this element, the length is just 3. This guy is calculating the direction vector for this element. So calculate direction vectors, and now these 4 statements are basically putting that value at the right location in that matrix. So right now matrix is still empty. Once I click 1, you can see that it has already put the correct number 1 at that location, at the correct location. So once I complete that, at this point, my first row of this matrix, the first row out here, is correct. There were 4 numbers, 1, 0, minus 1, 0. Those numbers have been added to this column. Okay, so I'll similarly keep on going. Loop 2, now I'm looking at element 2. So element 2 is connected to nodes 1 and 3. So which particular rows would it contribute to? Michael? 1, so it's connected to nodes 1 and 2. The equilibrium equations corresponding to nodes 1 and 3 would be equations 1 and 2 for node 1 and equations 5 and 6 for node 3, right? So if you again go back to those equilibrium equations, for node I, the equilibrium equations would be 2i and 2i minus 1. So if it's node 3, it would be 6 and 5, right? So that's exactly what this is doing. Let's run it here, and so I just ran through those lines without going into too much, without doing one by one. But clearly, column 2 is now correct. And if I run it one more time, you should be able to see that column 3. Sorry, where's my matrix? Right. So it's become bigger than I can show in one window, but at least you can see that column 3 is now correct, and it contributed to rows 3, 4, 5, 6. So the element 3 is connected to which nodes, Hongzi? This is node 2 and node 3, right? So, and clearly we can check with elements it's connected to nodes 2 and nodes 3. So similarly, if we keep on doing that, after 7 tries, I think this is the 7th. Yep, so this is the 7th. This would be the last time this loop runs. And once it ends, I have my matrix. The first 7 columns of that matrix are correct, have been input by this subroutine. And lastly, what we'll do is we'll see what the boundary conditions are. There are 3 boundary conditions for this problem. Node 1 is fixed in the 1 direction, that is the x direction. Node 1 is fixed in the 2 direction, which is y, and node 3 is fixed in the 1 direction, which is x, right? Those are the boundary conditions for this truss we are looking at. So one by one, we'll go through each of those boundary conditions, and if boundary condition 2 is equal to 1, that is if x is fixed, we need to go to the correct equation and put a 1 there. what is the correct equation? We need that correct equation would be 2n minus 1 because we are looking at node 1 x direction. So it'll go there and it'll put a 1, and the second boundary condition is node 1 direction 2, so it will go to this guy. And finally there is node 3x, so I'll do that as well. And at the end of this, now I have my complete matrix done. The first seven columns being all the way everything with member information, and the last three columns 8, 9, and 10 contain the informations from the reactions, which is basically what I was showing you. On this page of the handout. Now we have just built this entire matrix. We need to still build the right hand side vector, which is adding the external load to the correct location. So we'll do that. So that's exactly what this says: add the external load to the correct location. And without going through the details, I'll run through that. There's only one external load, and at this point I have my correct right hand side. There are two entries in there, minus 10 here and plus 10 here. Can anybody tell me why at these two particular locations? What do these represent, Miles? These are indeed the external load. So what would this minus 10 represent? X or Y direction? X direction. At node 2, X direction, I have a load of minus 10. Let's check. At node 2, X direction, it's minus 10 right now, because on the right hand, it will go to the right hand side and become a negative of negative. So that's why I've added it as a minus. And similarly, this 10 is at node 4 Y direction, right? This is the 8th entry in this. This is the 8th entry, so this is node 4 Y direction of 10. So again, we have a load here of minus 10, which will go to the right hand side and become plus 10. That's why it's plus here. So once we have that, this one line is us asking MATLAB, hey, I have this matrix. We've just constructed this matrix. We have just constructed this right hand side vector. Now give me the solution, right? Solving a 10 cross 10 system by hand would be cumbersome, but MATLAB takes no time. Just say that and it's done. And the solution for that is what, Nikhil? So when I'm solving this system by using this backslash operator, can you tell me what the solution represents? What are these numbers in this solution that I've just obtained? These are internal forces in the 7 members, and 3 other things are what? Those are the reaction forces. So these are indeed, these first 7 numbers right here are internal forces, and the last 3 numbers are the reaction forces. And we can check. So if I look at the solution, there seem to be quite a few zero force members also here, right? And the last 3 numbers are the reactions. And at this point, this code is done. It will send back. All that this subroutine does is it takes nodes, elements, boundary conditions, and loads, and it sends back element forces and support reactions. If you want it, it will also send back the matrix and the RHS. But for the particular call that I was showing you, I don't want that, and calculate that and go back to the main program. So this one line 28 in the main program that I was telling you about, it has solved the truss, gives me back element forces and support reactions. The rest is just plotting. Okay, the rest is just plotting. So I'll execute that line and we can check. It has plot the reactions. It is telling me that there's a 17.5 negative reaction this way that will balance out this 10 here and 7.5 here. There's a 10 pointing upwards here that will balance out this 10. There's internal forces 0, 0, 0 here in these three members, and the only internal forces, non-zero internal forces, are in these members. So in no time, it can solve this particular truss or any other truss, any other determinate truss. This is only 7 members. You can have 700 members and it wouldn't matter, right? Um, so at this point, what we would also generally want to do is to try to calculate the displacement or the displaced shape of that truss. So let's see how to do that. So the next part of the code, which is on the handout today on the separate sheet, is finding out displacements of each and every node of the truss using the virtual work method. So let's see how do we do that. Essentially what we'll do is we'll apply the virtual work method to find the displacements of each node. Anybody remember how did you do that by hand? How do you find displacements at a particular truss node, say x direction? How do you do that by hand? Apply a virtual load P prime, or just to make things simple for programming, we'll apply a unit load P prime at that node, and we'll measure all the virtual internal forces. How do I do that? How can I solve the truss for a unit load applied in the x direction? I've just shown you a program, right? We'll use the same program to solve for the internal forces for a unit load applied at one of the nodes. Then I'll apply a unit load at the y direction. Solve the same truss again. Go to the next node, apply x direction unit load, apply y direction unit load, and keep on repeating that for all the nodes. So that's exactly what this algorithm says. Go to a particular node, apply x direction load, measure internal forces, calculate internal virtual work done. Since the P prime that I'm applying is equal to 1, this internal virtual work done would be equal to the x displacement, right? So let's see how that is being computed. So number of nodes is just a variable that I'm creating here. And here's the for loop that's starting. I think in your handouts, this for loop is right here. Bless you. So we have this for loop all the way out to here. So everything between this for and this end, everything in here will repeat for each and every node. Okay, there are 5 nodes in here, so this process will be repeated 5 times. I'm saying virtual load is the current node x direction, the current node y direction. I'll solve that call. You see that call to solve truss 2D? With just one call, I'm solving that truss for internal forces, once for the x direction and once for the y direction. This is the virtual element forces for the x direction, virtual element forces for the y direction. Once I have that, compute ui prime. That is nothing but that n prime, calculating this formula. Sorry, where's that? Calculating this formula using that table that we used to build. That used to take so much time sometimes, right? But that entire table is being computed with this one command: dot product virtual element forces times real element forces times element lengths divided by EA, right? This part right here is n prime, and the rest out here is D, which is equal to, maybe I should write it in blue. That is the real displacement, D equal to NL over AE. So If I multiply those two and do a dot product over all of them, then that is doing a summation, right? This dot product is doing a sum of all of those things, once for the x direction, once for the y direction, and now I have those displacements. I can use those displacements to plot the deformed truss. So if I do that, I'll just let the code run through and run through that, remove the breakpoint and run through that, and I have the deformed truss. To plot this truss, can you tell me how many times did I have to compute the internal forces of this determinate truss? Say that again. 14. Once to find the actual internal forces due to the actual loads, and then there are 5 nodes. So 2 times 5, 10 times I solved that. So a total of 11, right? And if I don't want the displacements for the ones that are fixed, then we can remove that. Actually, we can optimize it a little bit, but there's no need. So in a click of a button, MATLAB has solved this truss 11 times. And of course, this is not something you can do by hand, right? Or you shouldn't do by hand. But and that's really the benefit of being able to really automate the process. So what did we do? I think if you look at the main most important part of the code, that most important part of the code was this guy, solve truss 2D. This is really the most important part of the code. And in this, you can see the only kind of trick that we used was to generate that A matrix and the right hand side. So if we can figure out how to generate this matrix automatically for any truss, and how to generate this right hand side for automatically for any truss, we can let MATLAB solve that problem or any other solve determinate truss problem. Maybe just to show you, I'll run this problem on all the different trusses I have in terms of input file. Input file 1, open, and it looks like this. So again, just with one click of a button, there was this truss with a 50 kilonewton load solved. I'll run it again with a different input file. Input file 2, boom, with one click, again, we've solved that truss. So if you can, the trick is really, for a new problem, you should be able to try to figure out an automatic way to convert your given problem into a system of equations that looks like this, and let MATLAB solve it. Okay, Drew?
So for like the homework and the quizzes, you said that we're gonna have to like make changes to it.
Correct.
What kind of changes are you talking about?
I'll show you. So sometimes you can have, I might give you an input file where I might say, hey, this member is maybe slightly short. How would you change this code to incorporate that? Right? Or I might say that this particular support point is not really either in X or in Y, but at an angle. How do you incorporate that? So those would be the small types of changes. But for that, in order to be able to do that, you would have to understand what's really going on. But you'll see, I'll come up with some questions, and of course, I'll be available to answer questions when you have them. All right, so that's part 1 of solving a statically determinate truss and then plotting all of the displacements. The next part of this is actually quite complicated, and I don't intend to go into too much detail about this. So I'll tell you what the algorithm is, and then I'll let you figure out how the code is actually doing. So this is on the other stapled big handout for today. This is basically doing systematic analysis using a force or a flexibility method for indeterminate trusses. Okay, this clearly right here is an indeterminate truss. I could have lots of loads, lots of boundary conditions. But no matter how high the degree of redundancy of indeterminate truss is, this program or this algorithm would help you solve it automatically. Something you remember you did a couple of problems on indeterminate trusses, how much work it can get, right? Just to cut a member, solve the actual loads, find the displacement at that cut, go back and find the flexibility at the cut, then over superimpose using the compatibility equation. There was only one compatibility equation. If the degree of redundancy is 1, there's only one compatibility equation that you're really solving. Here, what is the degree of indeterminacy of this truss? 6. 1, 2, 3, 4, 5, 6. 6 panels, all of them have a crosses. 6 is the degree of redundancy of this truss. You would have to do so many displacements and some things. Obviously, you cannot, well, you can, but you wouldn't want to do this by hand. Which also means that typically, if you have, let's say, n is the number of redundancy, you would have a n cross n system of compatibility equations, right? If you remember long back from the force method that when we had started, I gave you an example of this beam. If I have two redundant points, I'll have two compatibility equations and I'd be solving for two redundant unknowns, which is not something that I asked you to do by hand, but even with two, it becomes quite cumbersome. But with a computer method, doesn't matter how high the redundancy is. Once you figure out the algorithm, you can just apply it to any truss. Let's see how this works. So the idea here is still exactly the same. Consider this truss. What is the degree of redundancy of this truss? This degree of redundancy is also 2, right? Because if I remove that guy, this was the truss that we just solved. This was the determinate truss that we just solved. So if I add back that support, then I have added two redundant forces at that point. Clearly, degree of redundancy or indeterminacy is 2 here. So I can break this up into a underlying determinate truss that we had just solved, and plus a redundant problem where there are two redundants. So if I can solve this actual problem and a redundant problem, I can superimpose them together, and then I can get the solution to my indeterminate truss. And the way to do that would be the way to solve the actual problem. Now the actual problem is a determinate problem. We have just solved that system of equations, right? A n equal to minus f. We have just solved that system of equations. What we'll do is we'll do the same process for the redundant truss also. We'll go and apply a unit load at fx, solve that problem. Then we'll go apply a unit load to fy or 5y, solve the second redundant problem. And in general, there might be other redundant points. So for each redundant point, we'll be solving a system of equations, which is not a big deal because this is just solving a statically determinate truss. Even in this case and even in this case, each one of those rows is solving a statically determinate truss. One call to our magic subroutine, right? One call to this function. That's what this is. And we can do this redundant problem by putting it into a loop. And I think there if you look at this closely, what we are really doing is we are going to the correct degree of freedom for the redundant problem, adding a 1 to that location. This is 5x, this is 5y, and we are solving for the internal forces using the same system of equations that we had before. But okay, we'll stop here. We'll talk more details about this next time. And I think that should be it for the force method. And that will be before the quiz. And Friday we'll have a quiz. And after the spring break, we'll start with a new topic with the stiffness method, which is more of this programming, by the way. So, all right. So I'll see you back on Wednesday. Okay.
What is going to be on the quiz again?
It's basically Castellanos method for force for beams and frames, and force method.
Okay, what about math?
Homework 5. Not yet.
Okay.
Not yet. Yeah.